So this is the third part of this lecture, and I will discuss simple radiation models. And I have a pre-warning. This part contains mathematical equations. Okay? So maybe you have a little rest first and check this out a little bit later. But anyway, don't miss it, because it has very important conclusions at the end. So you learn quite a bit from this. Okay, so let's get started. So first of all, we look at the surface heat flux budget. Okay? Because what we want to know is what are the consequences if some component of the energy fluxes changes. For example, you change the solar radiation. What's the consequence of that? Say if you just increase it by 10%. What's the consequence? Or you change the terrestrial radiation. You make the Earth warmer and you increase the radiation that comes from Earth. Okay, so in order to understand that, we do it step by step, and we look at that one equation. So it's shown here, up in yellow, highlighted by yellow, and on the right-hand side are all energy fluxes that contribute to a net heat flux, a residual heat flux. On the left-hand side shows the residual heat flux, which is not zero if all the sum of these terms on the right-hand side are not zero. Okay, so we have the solar radiation, called our sun, and you know that's on average 240 watts per square meter. So whenever our sun appears, you don't need to worry about it, because you know it's 240 watts per square meter. Okay, so if I come tomorrow and I wake you up and I ask you, what is our sun? You wake up and you say it's 240 watts per square meter. So you have the terrestrial radiation, and this appears here in this equation with a minus sign. With a minus sign to illustrate that on its own it would induce a cooling of the surface, because the energy moves away. Okay, so this is the terrestrial radiation, plus we have other heat fluxes. For example, there can be radiation emitted by the greenhouse layer, the layer of greenhouse gases. And there can be other heat fluxes that we call latent and sensible heat fluxes, but we don't worry about it at all. We just call it other. Okay? All we want to know is what happens if the sum of these terms is positive, negative, or if it's zero. If it's zero, we have a balance, and zero means no change, no consequences at all. Okay, which is shown here as the last case. So let's look at first the case. The delta R is positive. It exceeds zero. What it means is that the medium heats up and the surface becomes warmer. That's easy, isn't it? If it's negative, means that the medium cools down and the surface becomes colder. But the key here is that the temperature change of the surface changes the terrestrial radiation. Okay? And if the terrestrial radiation changes, the residual heat flux changes. There is a feedback. Okay? There is an adjustment taking place. Before we talk about this in more detail, the first thing that we want to do is we want to express terrestrial radiation in terms of a formula in a more detail. We want to know what controls terrestrial radiation, the total amount of terrestrial radiation. Solar radiation, we know, 240 watts per square meter. What is now the formula for our Earth? Okay. Well, luckily there is the Stefan-Boltzmann law that you can use to calculate the total energy flux not only emitted by Earth but also by the Sun. Okay? But for the Sun we don't need to do it because we already know what it is. Okay? So, this is a formula from which you can calculate the total heat flux in watts per square meter, and you need to plug in the temperature in Kelvin, okay, expressed in the unit of Kelvin, and then to the power of 4. Okay. So this is important to convert it to Kelvin, otherwise your calculations are wrong. Okay. Then the sigma is a constant, which is a constant that never changes, is written here. And this epsilon is the emissivity, that tells us how efficient radiation is emitted. Okay. And the epsilon is, on average, very close to unity, to 1. For the Earth, on average, is 0.96. And we use this value in the following. Okay? So now you can calculate it. You can know, wow, you can see that temperature, the surface temperature, controls this terrestrial radiation. Okay, the next thing we do is now we'll plug this into the formula that we had. In order to understand a mechanism, an adjustment called the Planck adjustment, named after Max Planck, who made significant contributions to the understanding of heat fluxes. Okay. So now let's try to see what happens. So we have our formula again, and you can see that we have the terrestrial radiation in here with the temperature to the power of 4. So let's talk about these cases again. Okay, where we have delta R exceeds 0. Okay, so we have an imbalance, we have an anomaly, which implies that the surface becomes warmer. Well, the temperature increases, the T increases. In this formula here, the term without the minus increases, which lowers the delta R. Okay, and you can anticipate that this continues until delta R approaches 0, and then you have a balance again. So you have a disturbance, and then the temperature adjusts so that you get a balance again. Similarly, if you decrease, you have a negative value of delta R, you have some process which leads to a decrease of the net radiative forcing, and that implies that the surface cools down, the temperature decreases, this term without the 0 decreases, the total, the delta R increases until you go back to an equilibrium. And this is an adjustment process. So whatever disturbance you get in the climate system leads to a Planck adjustment. Okay? So the surface temperature adjusts to changes in the heat flux budget. And just as a little guide of how much, so if you get a change of 4 watts per square meter, you sort of can work out that this corresponds to a temperature change of 1 degree Celsius on average. Okay, this is a little guide, okay, that helps you to understand the link between heat flux anomalies and temperature changes. So this Planck adjustment is inherent in all climate feedback mechanisms. Therefore, I call it an adjustment and not a feedback mechanism. Okay, it is an adjustment process. All right, so that's the the very important, it's one of the most important principles required to understand climate changes, this Planck adjustment. And we assume it in the following. We assume that the temperature always adjusts to achieve a balance of the heat fluxes. Okay? And I just say it one more time. This Planck adjustment only exists because you have that counteracting process of terrestrial radiation, which turns up with a minus sign in this equation. All right, so now we go one step further. We want to understand the greenhouse effect. We want to work out how much does it actually change the global temperature. You know, we can assume that there are no greenhouse gases. We want to know what would be the equilibrium temperature on Earth. Or we can assume that the greenhouse gases absorb all terrestrial radiation. What would be the temperature? To this end, we produce a little sketch here. I'll produce a little sketch which includes the sun and the radiation by the sun, solar radiation called our sun. Can we just add some symbols to it? Here we name it our sun. We have the radiation emitted from the Earth's surface, our Earth. Okay, and then we go a little bit into more detail. Okay, so we know that the layer of greenhouse gases also emits. Okay, it starts to emit, it warms up, it starts to emit, and we now distribute the radiation that is emitted back to space into two parts. One component which is emitted by the Earth, okay, and the other one which is emitted by the greenhouse gases. And the one that is emitted by the greenhouse gases we call R green, okay, and the degree of absorption we call kappa. It's this kappa. So we have actually like a slider. We can slide this kappa. We can move. We can change between 0 and 1. The R sun, we don't need to worry about it at all because we know it's 240 watts per square meter. Okay, so what we then do, the next step, is to look at heat flux balances. Okay, here we only have radiation. Okay, we call it a radiation balance. And we can do that at two levels. We can do it at the top of the atmosphere and look at all the contributions that come in and that come out of the top of the atmosphere. So we have one contribution, our sun comes in, and we write it down. It's done here on the top. Our sun equals, and the other radiative fluxes leaving the top of the atmosphere are 1 minus kappa R Earth and kappa times R green. Okay? So this is our radiation balance at the top of the surface. At the top of the atmosphere, sorry. We can also construct a radiation balance at the top of the Earth's surface. Here, at the surface of Earth. Here we have incoming energy coming from the sun, and we have incoming energy coming from the greenhouse gases, this kappa R green, and we have outgoing radiation coming from the surface of Earth. And we can write it as a balance, okay, which is written here. Okay, that's the first part. We have to do a little bit more because we have too many unknowns in these two equations. We want to narrow it down a little bit. Okay, so let's do it on the next slide. Next slide, we write down both equations. And if we do that, we can see that both equations have the same term on the right hand side, the kappa times R green. It's on both sides, and we can actually substitute this term. We can put both equations together to get one equation, and the R green term disappears, and this is where we get our results. Okay, so we get that the radiation emitted by the Earth is 2 times radiation emitted by the Sun divided by, in brackets, 2 minus kappa. And then we can plug in different values of the kappa. For example, we learn that if kappa is 0, the amount of radiation that the Earth emits is the same as the energy it receives, 240 watts per square meter. Okay, that makes sense. For the maximum greenhouse effect, if we set kappa to 1 and plug it into that equation, what we learn is that the Earth emits 2 times the energy received by the Sun, of 480 watts per square meter. You can see the difference. One is the minimum and one is the maximum amount of energy emitted by the surface of Earth as a global average. So let's have a look at these 2 extreme cases, just to have a look how, to maybe understand it a little bit better. So first case is the case, and it's a little sketch above my head first. Where is it? Here it is, the mouse. It's the first case is without greenhouse gases. So you can take this simplified model and assume no greenhouse gases. Okay, so what you get is 240 watts coming in, 240 watts per square meter going out. Okay. And then you work it out with your little formula. You can work it out. You plug in the values, and you work out with your calculator, that the equilibrium surface temperature, called the emission temperature, if you plug in 240 into this formula, is minus 15 degrees Celsius. So without greenhouse gases, the world would be icy. Minus 15 degrees Celsius on average. Okay. This is the first extreme. If you look at the other extreme, which is shown here, okay, also the sketch shows you how it looks like with the 240 watts per square meter coming in, and with the greenhouse gases actually overtaking the emission into the atmosphere, to emitting 240 watts per square meter to space, but also 240 watts per square meter as back radiation, so that the surface actually has to emit 480 watts per square meter to achieve a balance. Okay, because of the Planck adjustment. And if you plug in 480 into this formula, and if you find a calculator that can work out the 4th square root, you actually get that the other extreme is the warmest possibility is plus 33 degrees Celsius. This would be a very hot world in this other extreme. If you play around with the equation, you can also calculate, and this is just added here as a little comment, okay, for the current climate, which has an average surface temperature of plus 15 degrees Celsius, that this corresponds to an energy flux emitted by the Earth of 375 watts per square meter, okay, and this is the wrong symbol here, a kappa of 75%, okay, which means 75% of absorption by greenhouse gases. All right, so you learn quite a bit by playing around with these simple radiation models. And the most important thing you learn is that only because of greenhouse gases do we live in a world that sustains life. Okay, it's only due to the greenhouse effect. And the greenhouse effect plays big roles. It absorbs 3/4 of terrestrial radiation and operates like a warm blanket around the Earth. Okay, so the study questions are: what are greenhouse gases? What do we mean by the atmospheric window? Okay. How cold would the Earth's climate be without greenhouse gases? What's the highest possible average temperature on Earth? What is the albedo feedback? Explain the Planck adjustment. Planck adjustment is a very, very important feature. Okay, so this concludes this lecture.